Imagine standing above a distant star, not looking at our sun, but at a faint yellow light, shining more than 1,000 light years away. Around this star, hidden in darkness, orbits a world we barely understand. A planet scientists once called Earth's cousin, a place that might hold oceans, clouds, and maybe even the conditions for life. Its name is Kepler-452b. Before we continue this journey, subscribe to Theories Before Sleep, where calm science and distant worlds slow the mind and carry you beyond Earth. Because Kepler-452b is not just another exoplanet. It is larger than Earth, older than Earth, and it orbits inside a region where liquid water could exist. But distance hides its surface. Light reveals only fragments of its story, and every new discovery raises more questions than answers. Tonight, we will explore what scientists truly know about this mysterious world, how it was discovered, what its atmosphere might be like, whether life could survive there, and why Kepler-452b may represent one of humanity's most intriguing cosmic possibilities. A quiet planet, a distant star, and a mystery written across the universe. Let's begin. Kepler-452b was not discovered by accident. It was found by a machine that never blinked, never slept, never looked away. For 4 continuous years, NASA's Kepler Space Telescope stared at one small patch of the sky, watching more than 150,000 stars at once. Its mission was simple in theory, but extraordinary in scale: to measure tiny drops in starlight that occur when planets pass in front of their stars. This method is called the transit method. When a planet crosses the face of its star, it blocks a fraction of the light. That dip is incredibly small, often less than 1%, sometimes far smaller than that. But when the same dip repeats again and again at regular intervals, it reveals something remarkable. A planet is there. Kepler-452b revealed itself this way, not through an image, not through direct observation, but through rhythm. Every 385 days, its star dimmed slightly, over and over again, a consistent signal, a repeating shadow. And when scientists analyzed the data, they realized they were seeing something unusual. This planet was orbiting inside the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. This immediately made Kepler-452b special, because most planets discovered by Kepler were either too close to their stars, scorched by extreme heat, or too far away, frozen in darkness. Kepler-452b sat in a rare position, not too hot, not too cold, balanced between extremes. And then came another detail: its star. Kepler-452b orbits a star known as Kepler-452, a yellow dwarf star similar in size and temperature to our Sun, slightly brighter, slightly older, but remarkably familiar. This mattered because planets orbiting stars like our Sun receive similar types of radiation, similar light spectra, similar energy distribution. That means Kepler-452b exists under conditions closer to Earth's than most known exoplanets. It was not orbiting a red dwarf with violent flares. It was not orbiting a massive blue star with short lifespan. It was orbiting something stable, something calm, something long-lived. This alone made scientists pause. Now consider its orbit. Kepler-452 takes 385 Earth days to complete one revolution around its star. Slightly longer than Earth's year. This suggests a similar distance from its star compared to Earth's orbit around the Sun. But the star itself is about 10% brighter, which means Kepler-452 likely receives slightly more energy than Earth does. This raises immediate questions. Is it warmer? Does it have oceans? Does it experience greenhouse effects? Could it be slowly heating over time? Because the star is older. Kepler-452 is estimated to be about 6 billion years old. That is roughly 1.5 billion years older than our Sun. Which means Kepler-452b has existed in its habitable zone for a very long time, longer than Earth has. This is important because life on Earth took billions of years to evolve from simple chemistry into complex organisms. A planet that has remained stable for extended periods has more time to develop complexity. If life were possible there, it would have had time to evolve. But here is where uncertainty begins. Kepler-452b is not Earth-sized. It is larger, about 1.6 times Earth's radius. This places it in a category scientists call super-Earths, planets that are larger than Earth but smaller than gas giants like Neptune. We do not yet fully understand this class of planets. Some super-Earths may be rocky like Earth. Others may have thick atmospheres. Some may be water worlds. Some may be mini Neptunes with dense gas layers. Without direct observation, we cannot see Kepler-452b surface. We do not know if it has continents. We do not know if it has oceans. We do not know if it has mountains. We do not know if it has clouds. We only know its size, its orbit, its star. Everything else must be inferred. An inference is fragile. Now consider gravity. A planet 1.6 times. Earth's radius likely has stronger gravity. Depending on its composition, surface gravity could be up to twice that of Earth. This would affect everything. Atmospheric retention, cloud formation, weather patterns, ocean behavior, biology. Stronger gravity allows a planet to hold thicker atmospheres, which can create stronger greenhouse effects. This could make Kepler-452b warmer than Earth, potentially much warmer, and that introduces a possibility. Kepler-452b may be closer to a super greenhouse state, not necessarily hostile, but not Earth-like. Now consider its location in the galaxy. Kepler-452b is about 1,400 light-years away from Earth. That distance is enormous. Light leaving Kepler-452b when early human civilizations were forming on Earth is only reaching us now. We are not seeing the planet as it exists today. We are seeing it as it existed in the distant past, which means any conclusions we make are delayed by cosmic time. This creates another layer of mystery. Even if Kepler-452b had oceans when the light left it, they could be gone now. Even if it had clouds, they could have changed. Even if it once had stable climate, that stability may not exist anymore. We are observing a frozen snapshot in time. Now think about habitability more carefully. The habitable zone does not guarantee life. It only means temperatures could allow liquid water. But water is not enough. A planet needs stable atmosphere, protection from radiation, magnetic field, chemical building blocks, geological activity, climate stability. Earth has all of these. Kepler-452b may have some, or none. We do not know. Now consider radiation. Kepler-452 star is older and brighter. Over time, stars gradually increase in luminosity. This means Kepler-452b may have received increasing radiation over billions of years. This could push it toward runaway greenhouse conditions, similar to what happened to Venus. Venus may once have had oceans, but increasing solar radiation caused water evaporation, trapping heat, creating extreme greenhouse effect, and turning the planet into a hot, hostile world. Kepler-452b may be approaching this threshold, or it may still be stable. We cannot yet measure its atmosphere directly. Now think about atmosphere detection. Because Kepler-452b is so far away, current telescopes cannot analyze its atmospheric composition in detail. We cannot detect oxygen. We cannot detect methane. We cannot detect water vapor signatures. We are limited to indirect measurements, which means Kepler-452b remains a candidate, not confirmation, a possibility, not evidence. But possibilities matter because they guide future exploration. They shape telescope missions. They influence research priorities. Kepler-452 represents a class of worlds that may be common in the galaxy, Earth-sized to super-Earth planets orbiting sun-like stars. This means that even if Kepler-452b itself is not habitable, others like it may be. Now consider the emotional impact of this discovery. When Kepler-452b was announced in 2015, it was widely reported as Earth's cousin, a second Earth, a potential new home. But this language is misleading. It creates expectations that science cannot yet support. Kepler-452b is not a second Earth. It is a distant world with unknown conditions, but it is close enough to Earth-like conditions to matter. It exists in a narrow window where life could theoretically survive, and that is rare. Now, consider what this discovery tells us about the universe. It suggests that Earth-like conditions may not be unique, that planets with similar orbital characteristics exist elsewhere, that the galaxy may contain many candidates for life. But it also reminds us of distance. Even if Kepler-452b were perfect for life, we cannot reach it. Not with current technology, not with near-future technology. At 1,400 light-years away, even traveling at the speed of light would take millennia, which means Kepler-452m is not a destination. It is a message, a signal from the cosmos that Earth-like environments may exist beyond our solar system. Now consider the limitations again. We know Kepler-452b's radius. We know its orbital period. We know its star type. But we do not know its surface temperature, its atmospheric pressure, its ocean coverage, its cloud systems, its geological activity, its magnetic field. We are studying shadows, not landscapes, patterns, not pictures. This is the challenge of exoplanet science. It requires patience. It requires inference. It requires caution. Now imagine standing on Kepler Kepler-452b. If it were rocky, if it had land, if it had atmosphere, the sky color could be different. The star may appear slightly brighter, the gravity heavier, the clouds thicker, the horizon curvature slightly altered. But this is imagination. Science has not confirmed these details, which makes Kepler-452b powerful, not because of what we know, but because of what we don't. It represents the boundary between detection and understanding, between possibility and proof, between hope and evidence. And this is where our journey truly begins. Because to understand whether Kepler-452 could support life, we must go deeper. We must examine its environment, its star, its energy balance, its potential atmosphere, and its long-term stability. Only then can we begin to answer the question that made this planet famous. Is Kepler-452b just another distant rock? Or is it one of the closest things we have ever found to another Earth? And that question leads us to the next part of this story. To understand Kepler-452b, we must move beyond its discovery and into the environment that shapes it. Because a planet is not defined only by its size or orbit. It is defined by the star it lives under. Everything begins with light. Kepler-452b orbits a star very similar to our Sun, a yellow dwarf, stable, long-lived, quiet compared to the violent red dwarfs that dominate our galaxy. This alone makes Kepler-452b unusual among potentially habitable exoplanets. Most Earth-sized planets discovered so far orbit red dwarf stars. These stars are smaller, cooler, and far more active. They release frequent stellar flares that can strip atmospheres and bombard planetary surfaces with radiation. Kepler-452's star is different. It produces steadier light, more predictable energy output, fewer extreme flare events. This stability matters for life. Life on Earth evolved under relatively consistent solar conditions. Sudden radiation spikes can damage DNA, disrupt ecosystems, and destabilize atmospheres. A calmer star creates a safer environment. But Kepler-452's star is also older. At roughly 6 billion years of age, it is entering a phase where stars slowly become brighter. Over time, the amount of energy reaching Kepler-452b has been increasing. This creates a long-term climate challenge. When stars brighten, planets in the habitable zone gradually receive more heat. What was once perfectly balanced can slowly drift toward dangerous warming. Earth is experiencing this effect very slowly. Over billions of years, our Sun will become brighter and eventually push Earth out of the habitable zone. Kepler-452b may already be closer to this tipping point. This raises the possibility that Kepler-452b is not just warm. It may be approaching a runaway greenhouse state. Now consider the planet itself. Kepler-452b is classified as a super-Earth. Larger than Earth, but not large enough to be a gas giant. This size range is one of the least understood categories of planets. We know Earth well, we know gas giants well, but super-Earths occupy an uncertain middle ground. Some are rocky, some are ocean worlds, some are covered by thick atmospheres, some resemble scaled-up versions of Earth, others resemble mini Neptunes. Without direct measurement, we cannot place A larger planet can retain more gas. Its stronger gravity allows it to hold onto hydrogen, helium, and heavier atmospheric molecules more efficiently than Earth. This could mean Kepler-452b has a thicker atmosphere. A thicker atmosphere can trap more heat. This creates stronger greenhouse effects, which could raise surface temperatures beyond Earth-like levels. However, thicker atmospheres can also protect against radiation and stabilize climate if balanced correctly. It depends on composition: carbon dioxide, water vapor, methane, nitrogen. Each behaves differently. Without spectroscopic data, we cannot know which gases dominate. Now consider internal structure. Kepler-452b's size suggests it may have a larger rocky core, higher internal pressure, and possibly stronger volcanic activity. Volcanism plays a major role in planetary habitability. On Earth, volcanoes recycle carbon, release gases into the atmosphere, and help regulate climate through long-term carbon cycles. If Kepler-452b has active geology, it could help stabilize its atmosphere. If it does not, its atmosphere could become stagnant or unstable. Now think about water. Water is central to life as we know it, but water presence is not guaranteed simply because a planet sits in the habitable zone. Water must be delivered during planet formation or retained over billions of years. Large planets can hold water more easily, but increased heat can evaporate oceans. This leads to water vapor accumulation in the atmosphere, strengthening greenhouse effects and accelerating water loss to space. This process may have happened on Venus. Kepler-452b could be walking a similar line. Now consider rotation. We do not know how fast Kepler-452b spins. Rotation affects climate. Fast rotation creates strong atmospheric circulation. Slow rotation can create extreme temperature differences between day and night. If Kepler-452b rotates slowly, one side may be hotter while the other cools, creating unstable climate zones. If it rotates quickly, it may distribute heat more evenly. Now consider axial tilt. Earth's tilt creates seasons. Seasons influence climate patterns, ecosystem diversity, and energy distribution. We do not know Kepler-452b's tilt. It could have mild seasons or extreme seasonal swings. This uncertainty adds complexity. Now consider magnetic fields. Magnetic fields protect planets from stellar wind and cosmic radiation. Earth's magnetic field shields our atmosphere and helps prevent atmospheric erosion. We do not know if Kepler-452b has a magnetic field. Magnetic fields require molten cores and planetary rotation. If Kepler-452b's core is active, it may generate a magnetic field. If not, its atmosphere could slowly erode over time. This is one of the most important unknowns. Now consider stellar wind. Even calm stars emit charged particles. Over billions of years, this wind can strip planetary atmospheres if magnetic protection is weak. Mars lost much of its atmosphere this way. Kepler-452b's stronger gravity helps retain atmosphere, but without magnetic protection, long-term erosion is still possible. Now think about timescale again. Kepler-452b has existed for billions of years, long enough for complex chemistry, long enough for climate shifts, long enough for geological cycles, long enough for potential life to evolve if conditions were right, but also long enough for potential collapse if conditions were wrong. We are observing it at one moment in its history. We do not know its past. We do not know its future. Now consider how scientists try to model this uncertainty. They use computer simulations. They estimate star brightness. They calculate orbital energy input. They simulate atmospheric compositions. They test temperature ranges. But these models rely on assumptions, and assumptions can be wrong, which is why Kepler-452b remains mysterious. Not because we lack curiosity, but because technology has limits. Now think about next-generation telescopes. Future observatories may be able to analyze exoplanet atmospheres in greater detail. They may detect water vapor, oxygen, carbon dioxide, methane. These molecules can provide hints of habitability or even biological activity. Kepler-452b is far away, making detection difficult, but not impossible in the long term. Now consider the psychological effect of this uncertainty. Humans want clear answers. Is there life? Yes or no? Is it habitable? Yes or no? But the universe does not offer simple answers. It offers probabilities, ranges, confidence levels. Kepler-452b sits in the middle of uncertainty. It is not confirmed to be habitable. It is not confirmed to be hostile. It is suspended between possibility and limitation, which makes it scientifically valuable. Now think about perspective. Before Kepler, we did not know how common Earth-like planets were. Now we know that planets in habitable zones are not rare. They exist across the galaxy. Kepler-452b is one example, one data point in a growing catalogue. It represents a population of worlds, not a single destination. Now consider the bigger implication. If planets like Kepler-452b are common, then Earth is not unique in terms of orbital conditions, but Earth remains unique in confirmed life, which suggests that habitability alone is not enough. Life requires more than position. It requires chemistry, stability, protection, time, and maybe chance. Kepler-452 reminds us that the universe can create Earth-like settings, but whether it creates life remains an open question. Now return to the quiet question that drives this entire topic. What are we truly searching for? Not planets, not data, but connection, evidence that life is not isolated to Earth, that the universe is not silent. Kepler-452 does not answer that question, but it moves us closer. It shows us where to look, what to look for, how to refine our tools, how to sharpen our understanding. And that is why this distant world matters, not because we can reach it, not because we can colonize it, but because it teaches us how to recognize worlds that might one day host life. And that journey continues, because to truly understand Kepler-452b, we must now turn to the most important question of all. Could life exist there? And if so, what form would it take? That is where our exploration leads next. When scientists speak about life on Kepler-452b, they are not imagining forests, animals, or cities. They are thinking about chemistry, because before life becomes complex, it begins as reactions, molecules interacting, energy flowing, patterns repeating. Life is not magic, it is physics guided by structure. And Kepler-452b forces us to ask a deep question. Does this distant world provide the conditions needed for chemistry to cross the threshold into biology? To answer that, we must begin with the most basic requirement: liquid water. Water is not just a solvent. It is a medium that allows molecules to move, collide, combine, and separate efficiently. It stabilizes temperature. It transports nutrients. It enables complex chemical networks. On Earth, every known living system depends on liquid water. Kepler-452b sits inside the habitable zone, meaning its distance from its star allows temperatures that could support liquid water. But this does not guarantee oceans. Water must be present, and water must remain stable. Planets can lose water through evaporation, through atmospheric escape, through chemical reactions that trap water in minerals. Kepler-452b's stronger gravity increases its ability to retain water. This is a positive sign. But higher energy input from its brighter star may counteract this advantage. This creates a delicate balance. Now consider atmosphere again. An atmosphere regulates surface temperature. It protects against radiation. It supports chemical cycles. Without an atmosphere, liquid water cannot persist on the surface. Kepler-452b likely has an atmosphere due to its size, but thickness matters. Too thin, and the planet loses heat at night and faces radiation exposure. Too thick, and greenhouse effects may trap too much heat. Venus demonstrates this extreme. Venus is similar in size to Earth, but has an atmosphere 90 times denser. The result is surface temperatures hot enough to melt lead. Kepler-452b could be anywhere along this spectrum. Now consider the possibility of oceans. Some super-Earths may be water worlds, planets covered entirely by deep global oceans. If Kepler-452b formed in a water-rich region of its star system, it may contain enormous quantities of water. This sounds promising, but deep oceans create challenges. Without land, nutrient cycling becomes difficult. Mineral exchange between rock and water may be limited. This can restrict biological complexity. Life could exist, but it may remain simple. Now consider energy sources. Life requires energy. On Earth, most energy comes from sunlight. Photosynthesis converts light into chemical energy. Kepler-452 receives slightly more energy than Earth from its star. This could support photosynthetic processes, but only if the atmosphere allows sufficient light to reach the surface. Thick clouds or haze could block sunlight. Alternatively, life could rely on chemical energy rather than light. On Earth, deep-sea organisms survive near hydrothermal vents, using chemical reactions rather than sunlight. If Kepler-452b has geological activity, similar environments could exist. This broadens the range of possible life environments. Now consider time. Kepler-452b's age is one of its most interesting features. It has existed in the habitable zone longer than Earth has. If conditions were stable, life would have had more time to evolve. This increases the probability of biological complexity. But stability is not guaranteed. Stars brighten over time. Planetary climates shift. Atmospheres change. Life requires not only suitable conditions, but consistent conditions. Long-term stability matters more than short-term habitability. Now consider radiation. Kepler-452's star is relatively calm. But cosmic radiation still exists. Without strong magnetic protection, surface life may be exposed to high radiation levels. This can damage DNA, but it can also drive mutation. On Earth, radiation contributes to genetic diversity. The key difference is dose. Low levels may accelerate evolution. High levels may prevent complex life from surviving. We do not know where Kepler-452 falls on this scale. Now consider gravity's effect on life. Higher gravity changes how organisms evolve. On a planet with stronger gravity, large upright structures become harder to support. Tall trees may be shorter. Animals may be stockier. Flying organisms may be rare or non-existent. This does not prevent life, but it changes its form. Kepler-452b, life, if it exists, may look very different from Earth life. Now consider atmospheric chemistry. Scientists search for biosignatures, chemical combinations that are difficult to explain without life. Oxygen paired with methane, ozone layers, nitrous oxide, certain organic molecules. If these gases are detected together, they suggest active biological processes. We cannot currently detect these on Kepler-452b. The planet is too distant, but future telescopes may improve this. Now consider the probability question. The galaxy contains hundreds of billions of stars, many host planets. A significant fraction of those planets lie in habitable zones. If life is rare, Kepler-452b may be lifeless. If life is common, Kepler-452b becomes a strong candidate. We do not yet know which scenario is correct. Earth is our only data point. One example. This creates statistical uncertainty. We are trying to understand a cosmic pattern from a single sample, which is scientifically difficult. Now consider the possibility of microbial life. Even if Kepler-452b is too harsh for complex organisms, microbial life could still exist. Bacteria-like organisms can survive extreme temperatures, high radiation, low oxygen, high pressure. They exist on Earth in deep oceans, acidic lakes, frozen ice, and radioactive waste. If water exists anywhere on Kepler-452b, microbes could potentially survive. This is one of the most realistic possibilities. Not intelligent life, not forests, not animals, but simple life, chemical systems that replicate and evolve. Now consider intelligent life. This requires far more conditions: stable climate for long periods, complex ecosystems, energy abundance, evolutionary pathways that favor intelligence. Kepler-452b may or may not provide this. We cannot assume intelligence simply because a planet lies in the habitable zone. Earth's intelligence is the result of many rare events: mass extinctions, environmental pressures, random evolutionary paths. Kepler-452b's evolutionary history is unknown. Now consider communication. Even if intelligent life existed on Kepler-452b, we would not detect it easily. Radio signals weaken over distance. At 1,400 light-years, communication becomes extremely difficult. Signals may not be directed at Earth. They may not use radio technology. They may not broadcast at all. Silence does not mean absence. Now consider the emotional aspect again. Humans want Kepler-452b to host life, because it would mean we are not alone, because it would make the universe feel alive. But science must remain neutral. It cannot project hope onto data. It must follow evidence. And currently, evidence is limited. Kepler-452b remains a candidate, a possibility, not confirmation. Now consider why this matters. The search for life is not just about aliens. It is about understanding biology, understanding how life begins, understanding whether life is a universal process or a rare accident. Kepler-452b 452 provides a test case. It allows scientists to study what conditions might support life, even without direct confirmation. Now consider the philosophical implication. If Kepler-452b hosts life, even simple life, it means life emerges wherever conditions allow. The universe becomes biologically active, not silent. If Kepler-452b is lifeless despite favorable conditions, it suggests life may be extremely rare. Earth may be special. This changes how humanity sees itself. Either outcome is profound. Now consider the future of this search. Future space telescopes will target exoplanets. They will analyze atmospheres, measure chemical signatures, study temperature patterns, detect cloud systems. Kepler-452b may one day reveal its secrets, but not soon. For now, it remains distant, quiet, unknown. Now imagine the possibility. Somewhere around that distant star, a world orbits silently. It may have oceans reflecting starlight, clouds drifting across its skies, chemical reactions happening beneath its surface. Or it may be barren, rocky, dry, silent. We do not know. And that uncertainty is what makes Kepler-452b powerful. It sits at the edge of our knowledge. It challenges us to build better instruments, ask better questions, think more carefully about life. And as we continue this exploration, another question emerges. Even if Kepler-452b could support life, how could we ever study it directly? How do we observe a world so distant? How do we move from shadows and signals to real understanding? That is the next step in this journey. To truly understand Kepler-452b, we must confront the greatest obstacle of all. Distance. Not emotional distance, not conceptual distance, but physical distance measured in light itself. Kepler-452b is located about 1,400 light-years away from Earth. That means the light we receive from this system today began its journey when human civilization was still in its early stages. Ancient cultures were building cities, writing was still developing, and yet the photons arriving in our telescopes now have been traveling through space uninterrupted for more than a millennium. This distance defines everything. It limits what we can see, what we can measure, what we can confirm. Unlike planets in our own solar system, Kepler-452b cannot be photographed directly with current technology. It does not appear as a visible disk. It does not show surface features. It does not reveal clouds or oceans. It exists only as a signal, a slight dip in starlight, a mathematical pattern, a shadow crossing a distant star. This is the reality of exoplanet science. We are not explorers walking on alien ground. We are observers reading faint cosmic fingerprints. Now consider how scientists extract information from this limited data. The transit method tells us the planet's size by measuring how much starlight is blocked. The larger the dip, the larger the planet. It also reveals orbital period. By measuring how often the dip repeats, scientists calculate how long the planet takes to orbit its star. From this, they estimate distance from the star. From distance and star brightness, they estimate temperature range. Everything builds on layers of inference. Each step introduces uncertainty, which means every conclusion comes with error bars, ranges, probabilities. Now consider atmospheric detection. For closer exoplanets, scientists sometimes analyze starlight that passes through planetary atmospheres during transits. Certain gases absorb specific wavelengths of light. By studying these absorption patterns, scientists can infer atmospheric composition. But Kepler-452b is far away. Its signal is weak. Its star is distant. The available data is limited. At present, we cannot perform detailed atmospheric spectroscopy on Kepler-452b, which means we cannot detect oxygen. We cannot detect methane. We cannot detect water vapor. We cannot confirm clouds. We cannot confirm surface pressure. This leaves us with models, computer simulations, theoretical climate scenarios. Now consider how models are built. Scientists input estimated planetary size, orbital distance, star brightness, and potential atmospheric compositions. They then simulate how heat would distribute across the planet. They test scenarios: thin atmosphere, thick atmosphere, high carbon dioxide, low carbon dioxide, high water vapor, low water vapor. Each produces different outcomes. Some models show Earth-like temperatures. Others show extreme greenhouse conditions. Others show unstable climates. This range highlights uncertainty. Kepler-452b may be temperate, or it may be hostile. Now consider technological limitations. Even the most powerful telescopes today struggle to observe Earth-sized planets around distant sun-like stars. Light from the star overwhelms the faint signal from the planet. Separating planetary light from stellar glare is extremely difficult. Future telescopes may improve this. Large space-based observatories, advanced coronagraphs, star shade technology. These tools may allow direct imaging of exoplanets, but these missions are complex, expensive, decades away. Kepler-452b sits at the edge of what is currently possible. Now consider interstellar travel. Even if we wanted to send a probe, it is not realistic. At current spacecraft speeds, traveling 1,400 light-years would take tens of thousands of years. Even optimistic theoretical propulsion concepts cannot bridge this gap within human lifetimes, which means Kepler-452b will remain unreachable. Not just difficult to reach, impossible with foreseeable technology. This forces humanity to rely on observation rather than exploration. Telescopes instead of spacecraft, signals instead of samples. Now consider communication. If life existed on Kepler-452b and attempted to communicate, signals would take 1,400 years to reach Earth. Any reply would take another 1,400 years. This creates timescales beyond human civilization, beyond political systems, beyond technological continuity, which means meaningful communication is unlikely. Now consider the psychological effect of this distance. Humans evolved to explore physically, to touch, to move, to travel. Kepler-452b challenges this instinct. It forces us to accept that some worlds will remain permanently distant, known only through light and mathematics, which reshapes how we think about exploration. Now consider the difference between knowing and experiencing. We can know Kepler-452b's orbit. We can estimate its size. We can model its temperature, but we cannot experience its environment. We cannot feel its gravity. We cannot see its sky. We cannot sample its atmosphere. This creates a scientific boundary, a limit where knowledge becomes abstract. Now consider how scientists push against this boundary. They search for patterns across many exoplanets. Instead of focusing on one world, they analyze populations. They study how planets behave statistically, how common super-Earths are, how often habitable zone planets appear, how star types influence planetary systems. Kepler-452b becomes one data point among thousands. It helps build broader understanding, even if its individual details remain unknown. Now consider the importance of comparison. Kepler-452b is compared to Earth, but Earth is not the only reference. Scientists also compare it to Venus, Mars, super-Earths, mini-Neptunes. This comparative approach helps narrow possibilities. If Kepler-452b's density were known, scientists could determine whether it is rocky or gaseous. But we do not yet know its mass. Mass measurements require gravitational interaction data. Kepler-452b's system does not provide clear radial velocity signals, which leaves density uncertain. Without density, composition remains uncertain. Now consider star variability. Even calm stars experience subtle changes: magnetic cycles, brightness fluctuations, stellar winds. Over billions of years, these changes affect planetary climates. Kepler-452 star may have undergone variations that influenced Kepler-452b's atmosphere. We cannot reconstruct this history precisely, which adds uncertainty. Now consider planetary formation history. Where did Kepler-452b form? Did it migrate inward from farther away? Did it form near its current orbit? Migration affects composition, water content, atmospheric retention. If it formed far from the star, it may be water-rich. If it formed closer, it may be drier. Migration is common in planetary systems, which complicates habitability assumptions. Now consider moons. Large planets often host moons. Moons can influence tides, climate stability, axial tilt. Earth's moon stabilizes Earth's tilt, reducing extreme climate swings. Kepler-452b may or may not have moons. We cannot detect them, but their presence could significantly affect climate. Another unknown. Now consider scientific patience. The search for life beyond Earth is not fast, it is incremental. Decades of observation, gradual technological progress, small discoveries building larger understanding. Kepler-452b represents a milestone, not because it answered questions, but because it revealed what is possible. It showed that Earth-like orbits exist around Sun-like stars. This shifted scientific expectations. It expanded the search. It motivated future missions. Now, consider public perception. When Kepler-452b was announced, headlines often exaggerated its similarity to Earth. This created excitement, but also misunderstanding. The public imagined oceans and continents, cities and life. Science never made these claims. It spoke in probabilities, possibilities, careful language. The gap between scientific caution and public imagination is wide, which creates confusion. Now consider the responsibility of communication. Presenting Kepler-452b accurately matters, not as a fantasy world, but as a scientific target, a distant candidate, a learning opportunity. Now imagine future observations, new telescopes analyzing starlight, detecting faint atmospheric signals, confirming or rejecting habitability indicators. Kepler-452b may one day move from mystery to classification, but even then, Many details will remain unknown because distance always limits resolution. Now consider what Kepler-452b ultimately represents. Not a destination, not a new home, but a mirror. It reflects humanity's curiosity, our desire to find life, our need to understand our place in the universe. It reminds us that Earth-like conditions may exist elsewhere, but it also reminds us of how rare direct access is. Now return to the quiet truth. We may never know what Kepler-452b truly looks like. We may never confirm life there, but the search itself matters because it pushes technology, refines theory, expands knowledge, and reshapes how humanity sees itself. Which leads to the next question. If Kepler-452b remains distant and unreachable, why does it still matter? Why do scientists continue searching for worlds like it? And what does this search say about humanity? That is where our journey continues next. To truly understand Kepler-452b, we must confront the greatest obstacle of all: distance. Not emotional distance, not conceptual distance, but physical distance measured in light itself. Kepler-452b is located about 1,400 light-years away from Earth. That means the light we receive from this system today began its journey when human civilization was still in its early stages. Ancient cultures were building cities. Writing was still developing, and yet the photons arriving in our telescopes now have been traveling through space uninterrupted for more than a millennium. This distance defines everything. It limits what we can see, what we can measure, what we can confirm. Unlike planets in our own solar system, Kepler-452b cannot be photographed directly with current technology. It does not appear as a visible disk. It does not show surface features. It does not reveal clouds or oceans. It exists only as a signal, a slight dip in starlight, a mathematical pattern, a shadow crossing a distant star. This is the reality of exoplanet science. We are not explorers walking on alien ground. We are observers reading faint cosmic fingerprints. Now consider how scientists extract information from this limited data. The transit method tells us the planet's size by measuring how much starlight is blocked. The larger the dip, the larger the planet. It also reveals orbital period. By measuring how often the dip repeats, scientists calculate how long the planet takes to orbit its star. From this, they estimate distance from the star. From distance and star brightness, they estimate temperature range. Everything builds on layers of inference. Each step introduces uncertainty, which means every conclusion comes with error bars, ranges, probabilities. Now consider atmospheric detection. For closer exoplanets, scientists sometimes analyze starlight that passes through planetary atmospheres during transits. Certain gases absorb specific wavelengths of light. By studying these absorption patterns, scientists can infer atmospheric composition. But Kepler-452b is far away. Its signal is weak. Its star is distant. The available data is limited. At present, we cannot perform detailed atmospheric spectroscopy on Kepler-452b, which means we cannot detect oxygen. We cannot detect methane. We cannot detect water vapor. We cannot confirm clouds. We cannot confirm surface pressure. This leaves us with models, computer simulations, theoretical climate scenarios. Now consider how models are built. Scientists input estimated planetary size, orbital distance, star brightness, and potential atmospheric compositions. They then simulate how heat would distribute across the planet. They test scenarios: thin atmosphere, thick atmosphere, high carbon dioxide, low carbon dioxide, high water vapor, low water vapor. Each produces different outcomes. Some models show Earth-like temperatures. Others show extreme greenhouse conditions. Others show unstable climates. This range highlights uncertainty. Kepler-452 may be temperate, or it may be hostile. Now consider technological limitations. Even the most powerful telescopes today struggle to observe Earth-sized planets around distant sun-like stars. Light from the star overwhelms the faint signal from the planet. Separating planetary light from stellar glare is extremely difficult. Future telescopes may improve this. Large space-based observatories, advanced coronagraphs, star-shade technology. These tools may allow direct imaging of exoplanets, but these missions are complex, expensive, decades away. Kepler-452b sits at the edge of what is currently possible. Now consider interstellar travel. Even if we wanted to send a probe, it is not realistic. At current spacecraft speeds, traveling 1,400 light years would take tens of thousands of years. Even optimistic theoretical propulsion concepts cannot bridge this gap within human lifetimes, which means Kepler-452b will remain unreachable, not just difficult to reach, impossible with foreseeable technology. This forces humanity to rely on observation rather than exploration. Telescopes instead of spacecraft, signals instead of samples. Now consider communication. If life existed on Kepler-452b and attempted to communicate, signals would take 1,400 years to reach Earth. Any reply would take another 1,400 years. This creates timescales beyond human civilization, beyond political systems, beyond technological continuity, which means meaningful communication is unlikely. Now consider the psychological effect of this distance. Humans evolved to explore physically, to touch, to move, to travel. Kepler-452 challenges this instinct. It forces us to accept that some worlds will remain permanently distant, known only through light and mathematics, which reshapes how we think about exploration. Now consider the difference between knowing and experiencing. We can know Kepler-452b's orbit. We can estimate its size. We can model its temperature. But we cannot experience its environment. We cannot feel its gravity. We cannot see its sky. We cannot sample its atmosphere. This creates a scientific boundary, a limit where knowledge becomes abstract. Now consider how scientists push against this boundary. They search for patterns across many exoplanets. Instead of focusing on one world, they analyze populations. They study how planets behave statistically, how common super-Earths are, how often habitable zone planets appear, how star types influence planetary systems. Kepler-452 becomes one data point among thousands. It helps build broader understanding, even if its individual details remain unknown. Now consider the importance of comparison. Kepler-452b is compared to Earth, but Earth is not the only reference. Scientists also compare it to Venus, Mars, super-Earths, mini-Neptunes. This comparative approach helps narrow possibilities. If Kepler-452 452b's density were known, scientists could determine whether it is rocky or gaseous. But we do not yet know its mass. Mass measurements require gravitational interaction data. Kepler-452b system does not provide clear radial velocity signals, which leaves density uncertain. Without density, composition remains uncertain. Now consider star variability. Even calm stars experience subtle changes, magnetic cycles, brightness fluctuations, stellar winds. Over billions of years, these changes affect planetary climates. Kepler-452's star may have undergone variations that influenced Kepler-452b's atmosphere. We cannot reconstruct this history precisely, which adds uncertainty. Now consider planetary formation history. Where did Kepler-452b form? Did it migrate inward from farther away? Did it form near its current orbit? Migration affects composition, water content, atmospheric retention. If it formed far from the star, it may be water-rich. If it formed closer, it may be drier. Migration is common in planetary systems, which complicates habitability assumptions. Now consider moons. Large planets often host moons. Moons can influence tides, climate stability, axial tilt. Earth's moon stabilizes Earth's tilt, reducing extreme climate swings. Kepler-452 may or may not have moons. We cannot detect them, but their presence could significantly affect climate. Another unknown. Now consider scientific patience. The search for life beyond Earth is not fast. It is incremental. Decades of observation, gradual technological progress, small discoveries building larger understanding. Kepler-452b represents a milestone, not because it answered questions, but because it revealed what is possible. It showed that Earth-like orbits exist around Sun-like stars. This shifted scientific expectations. It expanded the search. It motivated future missions. Now consider public perception. When Kepler-452b was announced, headlines often exaggerated its similarity to Earth. This created excitement, but also misunderstanding. The public imagined oceans and continents, cities and life. Science never made these claims. It spoke in probabilities, possibilities, careful language. The gap between scientific caution and public imagination is wide, which creates confusion. Now consider the responsibility of communication. Presenting Kepler-452b accurately matters, not as a fantasy world, but as a scientific target, a distant candidate, a learning opportunity. Now imagine future observations. New telescopes analyzing starlight, detecting faint atmospheric signals, confirming or rejecting habitability indicators. Kepler-452b may one day move from mystery to classification, but even then, many details will remain unknown because distance always limits resolution. Now consider what Kepler-452b ultimately represents. Not a destination, not a new home, but a mirror. It reflects humanity's curiosity, our desire to find life, our need to understand our place in the universe. It reminds us that Earth-like conditions may exist elsewhere, but it also reminds us of how rare direct access is. Now return to the quiet truth. We may never know what Kepler-452b truly looks like. We may never confirm life there. But the search itself matters because it pushes technology, refines theory, expands knowledge, and reshapes how humanity sees itself, which leads to the next question. If Kepler-452b remains distant and unreachable, why does it still matter? Why do scientists continue searching for worlds like it? And what does this search say about humanity? That is where our journey continues next. Even though Kepler-452b is unreachable, invisible in detail, and wrapped in uncertainty, it still matters. Not because we will ever stand on its surface, but because it changes how humanity understands the universe. Every discovery of a potentially habitable world reshapes a fundamental assumption. For most of human history, Earth was believed to be unique. Not just special, but alone, the only place where life could exist. Kepler-452b challenges this idea. It shows that planets with Earth-like orbits exist around Sun-like stars. It suggests that the conditions that made Earth possible are not isolated accidents. They may be part of a larger cosmic pattern. Now consider what this means psychologically. Humans have always searched for connection. In the sky, in the stars, in myths and science. The discovery of worlds like Kepler-452b feeds a deep curiosity. Are we alone? Is life rare? Or is the universe filled with living systems we cannot yet detect? Kepler-452b does not answer this question, but it brings it closer to science rather than speculation. Now, consider the scientific shift this represents. Before the Kepler mission, scientists had detected only a small number of exoplanets. Most were large gas giants, hot Jupiters orbiting extremely close to their stars. These planets were easy to detect, but they were not Earth-like. Kepler changed this. By observing continuously and precisely, it revealed thousands of smaller planets, planets closer to Earth's size, planets in habitable zones. Kepler-452b became one of the most important examples of this new category. It showed that Earth-sized and super-Earth planets in Earth-like orbits exist. This expanded the search for life. It changed telescope design priorities. It influenced mission planning. It redirected funding and research focus. Now consider how this affects future exploration. Scientists now design telescopes specifically to detect atmospheric signatures. They want to measure oxygen, methane, carbon dioxide, water vapor. These gases provide clues about biological activity. Kepler-452b helped motivate this direction. It became a reference point, a reminder that habitable zone planets are not theoretical. They exist. Now consider the technological ripple effect. To study distant planets, humanity develops better sensors, more precise detectors, advanced optics, artificial intelligence for data analysis. These technologies do not benefit astronomy alone. They improve imaging systems, communication networks, data processing. They spill into medicine, climate science, engineering. Kepler-452b indirectly contributes to this progress. Now consider the educational impact. Students learning astronomy today grow up knowing that Earth-like planets exist. This changes how young scientists think. It expands imagination. It motivates careers in physics, astrobiology, engineering, planetary science. Kepler-452 becomes part of scientific culture, not as a place, but as a symbol. Now consider the philosophical effect. If Earth-like planets exist elsewhere, then Earth is not cosmically unique, but Earth is still biologically unique, at least as far as we know. This creates a strange balance. The universe may create many Earth-like environments, but life may still be rare, or difficult, or fragile. Kepler-452b forces humanity to to confront this uncertainty. Now consider the emotional side again. There is comfort in knowing that Earth-like conditions exist elsewhere. It reduces the sense of isolation. It makes the universe feel more familiar. But there is also discomfort, because it highlights distance, separation, the inability to reach these worlds, which reminds humanity of its limitations. Now consider the deeper meaning of this search. Why do humans look for life beyond Earth? Not because of colonization, not because of escape, but because of identity. Understanding whether life is common or rare changes how humanity sees itself. If life is common, Earth becomes one example among many. If life is rare, Earth becomes incredibly precious. Either outcome increases responsibility. If life is common, we must protect it. If life is rare, we must preserve it. Kepler-452b contributes to this conversation. Now consider the idea of cosmic perspective. When humans observe distant planets, they are forced to see Earth from outside, not as a center, but as one planet among billions. This perspective reduces ego. It encourages humility. It emphasizes interconnectedness. Astronauts describe this effect when viewing Earth from orbit. Exoplanet science creates a similar effect intellectually. Kepler-452b helps produce this shift. Now consider the long-term future. In centuries or millennia, humanity may develop technology far beyond today's capabilities. Interstellar probes, advanced propulsion, artificial intelligence-driven exploration. Even then, Kepler-452b will likely remain difficult to reach. But data collection may improve. Atmospheric analysis may become routine. Surface mapping may become possible. Kepler-452b may eventually move from mystery to model, from unknown to partially understood, but it will always remain distant. Now consider what that distance teaches. It teaches patience, acceptance of limits, scientific humility. It forces humanity to rely on indirect observation, inference, probability. It reminds us that not all questions can be answered quickly. Now consider how this affects Earth science. Studying exoplanets improves understanding of planetary climates, atmospheric dynamics, greenhouse effects, magnetic fields, radiation shielding. These lessons apply directly to Earth. Climate modeling improves. Atmospheric chemistry becomes better understood. Planetary comparisons provide context. Kepler-452b indirectly improves Earth science. Now consider the symbolic value again. Kepler-452b is often described as Earth's cousin. This metaphor is powerful. It suggests similarity, but also difference. Cousins share traits, but live separate lives. Kepler-452b and Earth may share orbital characteristics, but their histories are different. Their environments may be very different. This reminds us that small differences in initial conditions lead to dramatically different outcomes. This is true for planets and for civilizations. Now consider the story of planetary evolution. Earth remained habitable. Mars lost its atmosphere. Venus became hostile. These three planets formed in the same solar system from similar materials, yet their outcomes diverged. Kepler-452b may represent another branch in this planetary family tree, one whose outcome we cannot yet see. This reinforces how fragile habitability is, how narrow the conditions must be. Now consider the role of chance. Life on Earth may have required rare events, specific chemical reactions, asteroid impacts that reshaped ecosystems, plate tectonics, magnetic field generation, stable orbit. These factors combined in a unique way. Kepler-452b may or may not share this history. Chance matters, which makes predictions difficult. Now consider the human narrative again. Humans often want certainty, answers, clear conclusions. Kepler-452 offers none. It offers possibility, probability, open questions. This is uncomfortable, but it is honest. Science rarely provides final answers. It provides better questions. Now consider what this means for the future of the search for life. The search will not end with one planet. It will expand to thousands, millions. Statistical patterns will emerge. Habitable zones will be mapped. Atmospheric biosignatures will be catalogued. Kepler-452b is part of this early phase, a stepping stone, not a conclusion. Now consider the quiet truth. Even if Kepler-452b is lifeless, it still matters, because it teaches humanity what conditions are not enough, what combinations fail, what factors are missing. This negative knowledge is just as important as positive discoveries. Now imagine the universe from a different perspective. Hundreds of billions of galaxies, each with billions of stars, each potentially hosting planets. Kepler-452b is one tiny point in this vast network, yet it carries meaning because humans discovered it, measured it, named it. It represents the moment humanity began to map the habitable universe. Now consider the emotional ending of this part. Somewhere in the darkness, Kepler-452b continues to orbit its star, silent, unaware of our telescopes, unchanged by our curiosity. It may host oceans, or deserts, or frozen landscapes. It may be alive, or barren. We do not know, but its existence has already changed humanity. It has expanded our understanding of what is possible. It has pushed science forward. It has reminded us that Earth-like conditions are not unique, but life itself may still be rare, and that makes Earth more precious, which leads to the next step of this journey. If Kepler-452b cannot be reached, if its secrets remain hidden, what does this mean for humanity's future in space? How do these discoveries shape our plans, priorities, and responsibilities? That is where the story continues. As the picture of Kepler-452b becomes clearer, another realization slowly forms. This distant world is not just an object of study. It is a turning point, because discoveries like Kepler-452b are quietly reshaping how humanity plans its future in space. For decades, space exploration was focused on our own solar system, the Moon, Mars, the outer planets, asteroids. These destinations felt reachable, close enough to touch, close enough to imagine as future homes. But Kepler-452b belongs to a different category. It is not nearby. It is not reachable. It exists on interstellar scales, and this forces humanity to think differently, not about colonization, but about observation, not about travel, but about understanding. And consider the shift in scientific priorities. Instead of asking, where can we go next? Scientists are increasingly asking, where can life exist? This is a subtle but powerful change. It moves the focus from movement to meaning, from expansion to knowledge. Kepler-452 helped accelerate this shift. It showed that Earth-like orbital conditions exist far beyond our reach. which means the universe may contain many habitable environments. But humanity may never physically visit most of them. This changes the goal of exploration. Now consider telescope development. Future space missions are being designed not to carry humans, but to carry instruments, powerful cameras, spectrometers, infrared detectors, light filtering systems. These tools will search for atmospheric signatures. They will analyze chemical compositions. They will detect water vapor, oxygen, carbon dioxide, methane. Kepler-452b represents the type of world these missions target, not as a destination, but as a test case. Now consider the idea of remote exploration. Humanity is entering an era where discovery does not require physical presence. Robots explore Mars. Telescopes explore distant galaxies. Data streams replace footsteps. Kepler-452b fits into this model. We explore it through light, through numbers, through probability, not through landing sites. Now consider the emotional adjustment this requires. Humans evolved to explore physically, to move across landscapes, to touch and build. Remote exploration feels abstract, less heroic, less dramatic, but it is more realistic for interstellar science, and it may be more powerful because it allows humanity to study thousands of worlds at once, not just one. Now consider the role of artificial intelligence. As exoplanet data grows, humans cannot analyze it alone. AI systems are increasingly used to detect patterns, identify transit signals, filter noise, model atmospheres. Kepler-452b was discovered using advanced data analysis techniques. Future discoveries will rely even more on machine learning. This means the search for life is becoming a collaboration between human curiosity and artificial intelligence. Now consider how this changes civilization. Scientific knowledge spreads faster. Global collaboration becomes essential. Astronomers across continents share data. Research becomes international. Kepler-452b was discovered through cooperation between engineers, scientists, programmers, and institutions. This represents a new model of exploration, not national conquest, but shared discovery. Now consider how this affects humanity's self-image. For much of history, humans believed Earth was the center of the universe. Then we learned Earth orbits the Sun. Then we learned the Sun is one star among billions. Now we are learning that Earth-like planets may be common. This continues the process of decentralization. Humanity is no longer at the physical center of anything. But this does not reduce significance. It changes meaning. Value no longer comes from central position. It comes from consciousness, from awareness, from responsibility. Now consider the ethical implications again. If life exists elsewhere, humanity becomes part of a larger biological network, not isolated, not unique. This raises questions about protection, non-contamination, respect for alien ecosystems. Kepler-452b may never be visited, but planets closer to Earth may be, and the principles developed now will guide future actions. Kepler-452b contributes indirectly to this ethical framework. Now consider humanity's long-term goals. Should the goal be to spread across the galaxy, or to understand the galaxy? Kepler-452b suggests that understanding may be more realistic than physical expansion, at least in the near future. The speed of light sets a limit. Energy requirements set limits. Biology sets limits. But knowledge has fewer constraints. Information can travel, ideas can spread, understanding can grow. Now consider what this means for culture. Stories about space may change. Instead of focusing only on colonization narratives, they may begin to focus on observation, connection, cosmic perspective, quiet discovery. Kepler-452b fits into this calmer narrative. Not dramatic invasion, but patient study. Now consider education again. Future students will learn that habitable planets exist far away, but they will also learn that distance matters, that not every discovery leads to immediate application. This teaches patience, scientific discipline, critical thinking. Now consider how this affects Earth priorities. As humanity discovers more habitable zone planets, Earth becomes more valuable, not less, because Earth remains the only confirmed living world, the only place with proven ecosystems, the only planet where humans can survive naturally. Kepler-452 does not reduce Earth's importance, it increases it, because it shows how rare confirmed life still is. Now consider the possibility of disappointment. If future telescopes analyze Kepler-452b's atmosphere and find no biosignatures, some may feel disappointed. But science does not lose value from negative results. Negative results refine understanding. They help eliminate false assumptions. They teach us what conditions are not enough, which improves future searches. Now consider the emotional rhythm of discovery. There will be excitement, then correction, then refinement. This is the natural cycle of science. Kepler-452b is currently in the excitement phase. Future research may bring more cautious conclusions, but each step moves humanity closer to truth. Now consider the scale of time. Human civilization is young. Exoplanet science is even younger. Only a few decades old. We are at the beginning of this journey. Kepler-452b is part of the early map, not the final destination. Now consider the role of curiosity. Curiosity drives exploration, not profit, not conquest, not competition. The desire to know what exists beyond Earth is deeply human. Kepler-452 satisfies this curiosity partially. It shows that Earth-like orbits exist, but it leaves many questions unanswered, which fuels further exploration. Now consider the quiet beauty of this process. Light traveling for 1,400 years reaches our instruments. Scientists analyze tiny fluctuations. Mathematics reveals hidden worlds. No explosions, no dramatic arrivals, just patient observation. This is how modern space discovery happens. And Kepler-452b is a perfect example. Now consider the long arc of history. One day, humanity may look back at the early 21st century as the moment when the first true catalogue of habitable zone planets was created. Kepler-452b will be listed among the pioneers, one of the first Earth-like orbit discoveries, a historical marker, not because of what it was, but because of what it represented. Now consider the emotional closing of this part. Somewhere far away, Kepler-452b continues its quiet orbit. Its star rises and sets across its surface. Clouds may drift, oceans may move, or deserts may stretch endlessly. We do not know, but we know this. Its existence has already changed how humanity sees the universe. It has shifted focus from isolation to possibility, from certainty to curiosity, from local thinking to cosmic perspective. And that shift is shaping the future of space exploration, not through rockets, not through colonies, but through knowledge. Which leads us to the next question. If Kepler-452b is shaping humanity's perspective, what does this discovery ultimately say about us? About our need to search, our need to understand, and our place in a universe filled with silent worlds. That is the final layer of this journey. When all the science is placed aside for a moment, when equations fade and data charts disappear, Kepler-452b leaves behind something deeper, a question about humanity itself. Because the search for distant worlds is not only about planets, it is about identity. It is about what humans are trying to find when they look into space. For thousands of years, people looked at the stars and imagined meaning, gods, destiny, guidance, stories written across the sky. Modern science replaced myths with measurements, but the emotional drive remained the same. Humans still look upward, searching for connection. Kepler-452b fits into this ancient pattern, not as a myth, but as a scientific mirror. Now consider what drives the search for life. It is not curiosity alone, it is loneliness. The idea that Earth may be the only living world creates a sense of isolation, a feeling that life is fragile and alone in an enormous universe. Finding planets like Kepler-452b softens this feeling. It suggests that environments capable of supporting life may exist elsewhere, even if life itself is not confirmed. This possibility changes how humans emotionally relate to the cosmos. Now consider the psychological effect of scale. Kepler-452 is 1,400 light-years away. This distance is almost impossible to imagine. Light travels nearly 300,000 kilometers per second and still needs more than a millennium to cross that space. This reminds humanity of its smallness, not in importance, but in physical scale. And yet, despite this smallness, humans can detect distant worlds. They can measure shadows across stars. They can calculate orbital periods. They can infer planetary sizes. This creates a powerful contrast. Humans are small, but capable of extraordinary understanding. Kepler-452b represents this balance. Now consider how this affects perspective. When people learn that Earth-like planets exist elsewhere, everyday problems shrink slightly. Borders feel smaller. Conflicts feel temporary. The planet itself feels more fragile. Astronomers often describe this effect. Seeing Earth as one planet among many creates humility, responsibility, a sense that humanity shares one home. Kepler-452b contributes to this shift. Now consider the danger of misinterpretation. Some people view discoveries like Kepler-452b as justification to abandon Earth, as proof that humanity can move on, that there is a backup planet waiting. This is a misunderstanding. Kepler-452b is not reachable, not livable with current technology, not a safety net. Using distant planets as psychological escape weakens responsibility. It shifts focus away from protecting Earth. Science does not support this narrative. Kepler-452 reinforces the opposite message. Earth remains unique, not because Earth-like planets do not exist, but because Earth is the only confirmed living world. Now consider responsibility again. If humanity is the only known intelligent life, that responsibility becomes enormous. It means Earth carries the universe's only known self-aware ecosystem. Protecting it becomes more than environmentalism. It becomes cosmic stewardship. Kepler-452b makes this idea more real by showing that habitable conditions may exist, but life itself is still unconfirmed. Now consider how this influences ethics. Future generations will judge today's actions, not based on how many planets were discovered, but on how Earth was treated. Climate stability, biodiversity protection, resource management. Kepler-452b does not reduce Earth's value. It amplifies it because it shows how rare confirmed life still is. Now consider the deeper emotional layer. Kepler-452b represents hope, not hope of escape, but hope of connection. The idea that life may not be isolated, that the universe may not be silent. This hope motivates science, drives funding, inspires students, encourages global collaboration. It is a quiet hope, not dramatic, but persistent. Now consider the cultural effect. Stories about space are changing. Earlier narratives focused on conquest. Planting flags, claiming new worlds, turning space into another frontier. But discoveries like Kepler-452b are slowly reshaping that story. They shift the narrative from ownership to understanding, from domination to observation, from expansion to awareness. Now consider how this changes the meaning of exploration. Exploration is no longer about reaching a place physically. It is about expanding knowledge, mapping invisible systems, understanding cosmic patterns. Kepler-452b cannot be visited, but it can be studied, and that study changes humanity's worldview. Now consider the role of patience. The search for life beyond Earth is not fast. It is not instant. It is measured in decades, in technological generations, in gradual improvement of instruments. Kepler-452 represents a step in this slow process, not a final answer, not a conclusion, but progress. And progress in science often looks quiet. Data analysis, model refinement, careful interpretation, no dramatic moments, no instant revelation, just steady movement toward understanding. Now consider how this affects trust in science. When discoveries are presented honestly with uncertainty and limitations, they build credibility. Kepler-452b is often misunderstood as another Earth, but scientists describe it carefully as a candidate, a possibility, not a guarantee. This honesty is important. It teaches the public how science actually works, not through certainty, but through evidence-based probability. Now consider how this influences global cooperation. Exoplanet research is not owned by one country. Telescopes are shared. Data is public. Researchers collaborate across borders. Kepler-452b was discovered by an international effort. This model of cooperation matters. It shows that some goals transcend national competition. Understanding the universe becomes a shared human project. Now consider the emotional shift this creates. Instead of seeing space as territory, people begin to see it as context, a larger environment that Earth exists within. This encourages planetary thinking, seeing Earth as a system, not as separate nations, not as divided regions, but as one fragile biosphere. Kepler-452b indirectly supports this mindset by reminding humanity that Earth is one planet among many, yet the only one known to host life. Now consider the contrast again. Kepler-452b may be similar to Earth in orbit, but Earth is alive. Kepler-452b may be silent. This contrast creates gratitude for breathable air, for liquid oceans, for protective magnetic fields, for stable climate, for ecosystems. Things humans often take for granted. Looking outward makes inward appreciation stronger. Now consider the risk of over-romanticizing distant worlds. Kepler-452b can easily become a symbol of fantasy, a dream world, a cosmic paradise. But science does not support this imagery. The reality is unknown, potentially hostile, possibly barren. This reminds humanity that fantasy should not replace responsibility. Now consider how this affects the next generation. Children growing up with knowledge of exoplanets will see Earth differently, not as the entire universe, but as one example. This can encourage curiosity, scientific interest, environmental awareness. It can also create existential questions. What is humanity's role? Why does life exist? Are we alone? Kepler-452 contributes to this philosophical shift. Now consider loneliness again. The universe is vast, mostly empty, mostly dark. Discovering planets like Kepler-452b does not guarantee companionship, but it suggests that the building blocks for life may exist elsewhere. This reduces the sense of cosmic isolation, even if no direct contact ever occurs. Now consider the future again. One day, humanity may discover clear biosignatures on an exoplanet. It may not be Kepler-452b. It may be closer or farther, but Kepler-452b helped prepare humanity for that moment. It introduced the idea of Earth-like orbital worlds. It trained scientists to think about habitability. It shaped instrument design. It built public interest. It is part of the foundation. Now consider what happens if life is never found. If decades of searching reveal no biosignatures, no confirmed alien life, Kepler-452b will still matter, because it will help confirm that life may be rare, that Earth is extraordinary, that preserving this planet is even more critical. This outcome would not make science meaningless. It would make Earth more precious. Now consider how this shapes values. If Earth is rare, humanity becomes responsible not just for itself, but for life itself, as far as we know. Kepler-452b strengthens this responsibility by showing that Earth-like conditions exist, but life itself remains elusive. Now consider the quiet emotional layer again. Somewhere far away, Kepler-452b continues to orbit. Its star shines steadily. Time passes. Millennia move forward. Civilizations rise and fall on Earth. Yet this distant planet remains unchanged by human awareness. It does not care if we discover it. It does not react to telescopes. It simply exists. This reminds humanity of humility. The universe does not revolve around us. We are observers, not controllers. Now consider what this does to ego. Human history is filled with ideas of central importance, chosen species, special destiny. But astronomy consistently reduces human centrality. Earth is not the center of the solar system. The sun is not the center of the galaxy. The galaxy is not the center of the universe. Kepler-452b continues this pattern. Earth-like conditions exist elsewhere, which means humanity is not cosmically unique in environment, but humanity may be unique in awareness, at least for now. Now consider awareness itself. Humans can think about distant worlds, reflect on cosmic scale, ask philosophical questions. This ability may be more important than physical expansion. Because understanding shapes behavior, not just movement. Kepler-452b encourages this deeper reflection. Now consider the emotional conclusion of this part. Kepler-452 is not a place to go. It is a place to think. It is a reminder that the universe is vast, that Earth is fragile, that knowledge is powerful, that curiosity defines humanity, and that searching for life is not just about aliens. It is about understanding ourselves, our limits, our responsibilities, our role in a universe filled with silent worlds. And as this journey continues, one final question remains. After all the science, the distance, the uncertainty, the hope, what does Kepler-452b ultimately teach humanity about its future? Not in space, but here, on Earth. That is where this story reaches its final layer, when the search for Kepler-452b finally circles back to Earth. It reveals something unexpected. The most important discovery was never the planet itself. It was the perspective it created, because Kepler-452b did not give humanity a new home. It gave humanity a new way of looking at its only home, Earth. For centuries, people believed that Earth was the center of existence. Then science showed that Earth is one planet among billions. Now exoplanet discoveries show that Earth-like orbits may be common, but life itself still appears rare. And that combination is powerful. It tells humanity that the universe can create the conditions for life easily, but life itself may be fragile, difficult, unlikely, which makes Earth extraordinary, not because it is alone in orbit time, but because it is alive. Now consider what this means for the future of civilization. If Earth is rare in life, then preserving it becomes more than environmental responsibility. It becomes existential responsibility. Protecting ecosystems is no longer just about comfort or economics. It becomes about protecting the only known living biosphere in the universe. Kepler-452b reinforces this by showing that similar environments exist, but not confirming life. Now consider the direction of progress. Many imagine progress as outward movement, more planets, more colonies, more territory. But Kepler-452b suggests another form of progress. Inner progress. Improving how humans live together. Improving sustainability. Improving cooperation. Improving wisdom. Because expanding into space without stabilizing Earth only spreads instability. It multiplies problems. It does not solve them. Now consider technological growth. Human technology is advancing rapidly. Artificial intelligence, automation, energy systems, space observation tools. These technologies can either accelerate destruction or accelerate preservation. Kepler-452b indirectly influences this choice by reminding humanity that Earth-like conditions are precious, that replacing them is nearly impossible. Now consider the lesson of planetary history. Mars once had rivers. Venus may once have had oceans. Earth remains stable. Small differences in planetary conditions created drastically different outcomes. Kepler-452b sits somewhere on this spectrum. It may be stable or unstable, habitable or hostile. This teaches humanity that planetary fate is sensitive to small changes, which makes Earth's climate stability even more important. Now consider climate change again. From space, Earth looks calm. Blue oceans, white clouds, green continents, but measurements show rising temperatures. changing weather patterns, melting ice, ocean acidification. Kepler-452b does not distract from this reality. It amplifies it because it shows what happens when planetary systems shift. Atmospheres thin, water disappears, habitability fades. Now consider what this means emotionally. Humans often feel disconnected from planetary scale processes. Climate change feels abstract, distant, slow. But when people understand that entire planets can lose habitability, the problem becomes more real. Kepler-452b helps create this understanding. It places Earth within a broader cosmic context. Now consider the responsibility of knowledge. Once humanity knows that Earth-like planets exist elsewhere, and that life may still be rare, it cannot ignore the value of its own planet. Ignorance disappears, responsibility increases. Now consider the idea of guardianship. Humanity may become the first species capable of understanding planetary systems deeply. That knowledge creates power, and power creates obligation. Obligation to protect ecosystems, to preserve biodiversity, to stabilize climate, to reduce pollution, to manage resources responsibly. Kepler-452b indirectly contributes to this shift by reminding humanity that life-supporting planets are not guaranteed. Now consider long-term thinking. Human civilization often operates on short timelines, decades, political cycles, economic quarters, but planetary processes operate on centuries, millennia, geological timescales. Kepler-452b exists on billion-year timescales. It forces humanity to think beyond immediate concerns, to consider long-term survival, not just of people, but of biospheres. Now consider education again. Future generations will grow up knowing that thousands of planets exist around other stars. They will learn that Earth is one example, not the only example of orbital stability, but still the only confirmed living world. This knowledge will shape values. It can encourage stewardship or indifference. The difference depends on how the story is told. Kepler-452b can be framed as escape or as reminder. Science supports the second interpretation. Now consider the danger of technological optimism. Some believe that technology will solve all planetary problems, that climate change can be reversed easily, that ecosystems can be rebuilt artificially, that damaged environments can be replaced. Kepler-452b shows how difficult it is to recreate planetary conditions. Even with advanced technology, building an Earth-like environment from scratch is nearly impossible, which means prevention matters more than repair. Now consider humility. The universe does not exist for humanity. It does not adapt to human needs. Planets evolve based on physics. Stars change brightness. Atmospheres escape. Magnetic fields weaken. Kepler-452b follows these natural processes. Earth is subject to them too. Humility reminds humanity that it is not in control of everything, but it can influence outcomes through behavior. Now consider cooperation. Planetary scale challenges cannot be solved by individual nations. Climate stability, ocean protection, atmospheric management, these require global coordination. Kepler-452b encourages planetary thinking, seeing Earth as one system, not fragmented territories. Now consider peace. When humans see Earth from space, borders disappear. Countries become invisible. The planet becomes one sphere. Kepler-452b strengthens this view. by placing Earth among other planets, not as separate nations, but as one shared world. Now consider meaning again. Humans often search for meaning in progress, expansion, achievement, but deeper meaning may come from preservation, from protecting life, from ensuring continuity. Kepler-452 does not promise a new beginning. It reminds humanity to protect what already exists. Now consider the emotional ending of this entire story. Somewhere far away, Kepler-452b continues to orbit its star. It does not know it has been discovered. It does not react to telescopes. It simply follows gravity, light, time. And yet, this silent world has influenced human thought. It has changed how scientists search for life, how engineers design telescopes, how students imagine the universe, how humanity sees its place among the stars. Now consider Earth again. Earth spins quietly. Oceans move, clouds form, life breathes, forests grow, animals migrate, cities glow at night. This planet is alive in ways no other confirmed world is. Kepler-452b shows that similar environments may exist, but none are proven alive, which makes Earth irreplaceable. Now consider the final realization. The search for life on Kepler-452b was never really about finding aliens. It was about understanding life itself, understanding how rare it may be, how fragile it is, how precious it becomes once recognized. And this understanding changes everything. It shifts humanity's focus from chasing distant dreams to protecting present reality, from imagining escape to embracing responsibility, from conquering space to becoming caretakers of life. Kepler-452b does not offer humanity a new world. It offers humanity a mirror, a reflection of what could exist, and a reminder of what already does. And perhaps that is its greatest gift. Not a destination, not a solution, but perspective. A quiet reminder that among billions of planets, this one matters most because it is home. And home is not something to abandon. It is something to protect now and for every generation that follows.